Previously, we had calculated the strength of the magnetic field at point A due to a single current-carrying wire, where the direction of the current was into the page. We said that the strength of the magnetic field at that point A would be 1 times 10 to the minus 6 teslas. And we also determined that the direction of the magnetic field would be down. This time we're going to use the concept of superposition to find the magnetic field at point A due to two conducting wires. And one thing that I'm going to add to this problem here is I'm going to add a coordinate system. That's really common for magnetism problems. We want to know what the positive x direction is, positive y direction, and also positive z, because we're dealing in many cases with three-dimensional phenomena. Alright, one other thing I'm going to add here is also let's make the distance between the wire and the point. Let's make that 1 meter for both wires. So what we're going to use is the same idea that we had used for electric fields, and that is the idea of superposition. That the total magnetic field will be due to the addition of the magnetic field contribution from wire 1, and that'll be added to the magnetic field contribution from wire 2. So let's call this one I1, and it has a current of 5 amps. And here we see that I2 is also carrying a current of 5 amps. At this point, we want to figure out what would be the direction of the field at point A due to the wire on the left. Luckily, we had already determined above that the direction due to that wire would be down. So I'm going to call this B1. It's the magnetic field contribution from wire 1. Now we have to figure out what would be the contribution from wire 2. So we may need to use the right-hand corkscrew rule, or perhaps the right-hand cross product rule, to figure out what that direction of field would be. On the side here, I'm going to draw magnetic field lines for both wires. We showed that the magnetic field due to the left wire would be circular in shape, and that the direction would be clockwise. And this meant that at point A, our field would be pointing directly down because we want our field to always be tangent to these concentric circles. If we do a similar kind of thing, a right-hand corkscrew rule for this current carrying wire, what we'll find is that it also makes a circular magnetic field, which would be oriented clockwise. So what would be the direction of the field at point A due to wire 2? Well, I hope it's clear that the direction would be up. This is B2 and this is B1. We know the distance here is 1 meter, and the distance here is also 1 meter. I think I can guess what the field is going to be, but let's just plug in nevertheless, just to show the steps. For our first contribution, we're going to want I1 for current of wire 1, and we can use D1 for this distance here. Over here, we're going to want mu naught times I2 over 2 pi D2. And this is D2. Now notice that I have a vector over my B on the left, but what I have here are actually not expressed as vectors. They're just single numbers. In order to express them as vectors, I actually want to add directional information in the form of unit vectors that would be appropriate for each of them. So for the contribution due to wire 1, we see that it's pointing down. And so that's going to be negative y. And so I'm going to put a negative j hat onto there. And that just tells me it's down rather than up. And that assigns a vector nature to this whole quantity now. For B2, we see that it's pointing upward. That would be this term here. We want to attach a positive j hat to that quantity. All right, this looks good. Now we have vectors. We need vectors because magnetic field, just like electric field, is a vector. Now let's plug in our numbers and get our final result. We can put the negative out front if we want here. 4 pi times 10 to the minus 7 could also be expressed as 4 pi with an e minus 7. And put our j hat there. All right, I think it's clear now that we're going to have 0 as our final magnetic field. So interestingly, at a point between two identical current carrying wires that are parallel like this, and they're carrying the current in the same direction, there's going to be a point between those wires where there's no magnetic field.